Hello dear students of plus one medical, non-medical, respected teachers. In this video I am going to discuss work done during an adiabatic process. Now what is an adiabatic process? It is that process in which no heat is allowed to enter or leave the system. That is dq is 0. Amount of heat supplied or amount of heat taken during an adiabatic process is 0. Now, to find expression for work done during adiabatic process, suppose we have a cylindrical vessel having perfectly non-conducting walls because no heat is allowed to enter or leave the system, and a frictionless piston containing 1 mole of an ideal gas at initial pressure P1, volume V1 and temperature T1. Let the gas is allowed to expand or gas is compressed so that volume changes, temperature changes. So by first law of thermodynamics, dq is equal to du plus dw. Since no heat is allowed to enter or leave the system, so dq is 0. Therefore, if dq is 0, dw is equal to minus du. So small amount of work done during small change is given by dw is equal to minus du. Now if Cv is equal to molar specific heat of the gas at constant volume, which is defined as the amount of heat required to raise the temperature of 1 mole of an ideal gas when volume is kept constant. So then by definition, Cv is given by Cv is equal to du by dt, or du is equal to Cv dt. So therefore dw is equal to minus Cv dt. So in terms of molar specific heat at constant volume, so we have dw is equal to this. Therefore, total amount of work done when temperature changes from T1 to T2. During adiabatic compression, temperature increases. During adiabatic expansion, temperature will decrease. So there will be change in temperature. So W is equal to minus integral T1 T2 Cv dt is equal to minus Cv. Cv can be taken as constant. So integral T1 T2 dt. Integral dt is dt. So therefore W is equal to minus Cv T limits T1 to T2. So solving it, we have minus Cv T2 minus T1, or rearranging negative sign inside. So W is equal to Cv T1 minus T2, which is the required expression for work done during an adiabatic process in terms of initial and final temperature T1 and T2, as well as molar specific heat Cv, which is constant for a given gas. Then by Mayer's relation, we have Cp minus Cv is equal to R. Here Cp is molar specific heat at constant pressure, which is defined as the amount of heat required to raise the temperature of 1 mole of ideal gas to 1 degree, 1 Kelvin at constant pressure. So Cp and Cv are related by this equation, Cp minus Cv, which is equal to R, which R is called gas constant, and this is known as Mayer's relation. Therefore, we can write Cp upon Cv minus 1 is equal to R upon Cv, divided by Cv throughout. But Cp upon Cv is equal to gamma ratio, which is always greater than 1. So Cp upon Cv, we have Cv is equal to R upon gamma minus 1. So substitute value of Cv in this equation number 2. So we have W is equal to R upon gamma minus 1 into T1 minus T2, which is another form of expression for work done during an adiabatic process. Also, if we take R inside this bracket, so we have W is equal to 1 upon gamma minus 1, R T1 minus R T2. And by ideal gas equation, we have PV is equal to RT. So P1 V1 will be equal to RT1, P2 V2 is equal to RT2. So instead of RT1 we substitute P1 V1, instead of RT2 we substitute P2 V2. So W is equal to 1 upon gamma minus 1 P1 V1 minus P2 V2, which is third form of work done during adiabatic process. So in this way we can derive expression for work done during an adiabatic process, because this relation will be used to find efficiency of Carnot cycle, that I will discuss in the next video. Till then, be happy, good luck, all the best, take care.